All right, and then the final process is basically a theoretical process, and we'll talk about why isothermal processes can't be real, but we can. But you'll see them; they're real on IB tests, so we got to take this seriously, right? Okay, so isothermal just means same temperature, so it's a constant temperature. And the question is, how do we have this happen? Because you understand that, let's say this is an an expansion, okay? If heat isn't allowed to flow in, we know that the temperature should drop, okay? So what we do is we do it very slowly. How slowly? Well, understand that any compression is going to raise that temperature, right? Because the piston has to move toward the gas. The particles have to bounce off going faster, right? So you could argue that isothermal processes can't happen, and you'd be correct. Except what we would say is that if we let it happen very slowly, like let's say it takes an infinite amount of time to do that, as the time it takes to do that approaches infinity, this process approaches isothermalness, okay? That is, it takes so long, right? And in my textbook, I totally didn't understand this, right? In my physics textbook, they showed a piston, and they were adding a grain of sand every year to the piston, I'm like, just get it over with, Okay, but so this is what we would say is that as the time it takes to do the process approaches infinity, this process will approach an isothermal process. So we do it in a piston. The piston's surrounded by this absolutely constant temperature reservoir that's well circulated, and as this thing moves out, the heat flows in so that the temperature doesn't drop. Okay. Now, if we look at the sort of the energetics of this thing, right? Okay. We can use just whatever that law is, PV equals PV, because the T is the same, right? You could say PV over T is PV over T, but the temperature stays the same, so you can cancel that out. So we can say PV equals PV, right? And then if you look at this, right, if we have an expansion, we can do Q equals change in internal energy plus work. Well, if the temperature is constant, then the change in internal energy is zero, okay? Because, remember, the internal energy is intrinsically tied to the temperature. If the temperature doesn't change, the internal energy doesn't change. So this guy's zero, okay? So if we look at an adiabatic expansion, that's positive work. Therefore, heat has to flow in, right? And so the net effect of the process after an infinite number of years is that a certain amount of heat is turned into a certain amount of work entirely. This, by the way, violates something like the second law of thermodynamics, right? So if we had an infinite amount of time, the second law goes down, okay? But, until then, we generally, regard the second law as actually true, okay? Now, let's imagine that we have an isothermal compression, right? Well, remember, compressions necessarily increase the temperature of the gas, right? Okay, so as the piston moves in, it's got to hit those particles. It's got to make them go faster, but it does it so slowly, again, that the temperature remains constant, right? So if we look at the energetics of this thing, okay, this is zero. The internal energy doesn't change. We have compression is negative work, and therefore heat flows out. Okay, we have negative heat, right? So heat is flowing out of the gas. We just push on this, heat flows in, heat flows out, right? Just understand that it takes an infinite amount of time. It's not practical. Infinite time is required. And then the final thing I'll give you is one of the things IB likes to do is they'll say, let's say this is an expansion. They'll say, show that it's isothermal, right? Well, here's how you do it, right? For an isothermal process, PV equals PV, right? Notice that this is at 6 times 2. 6 times 2, even, 10 to the 5th and 10 to the minus 3rd, right? 6 times 2 is 12. Right, that's P times V, right? If we look at this spot here, 4 times 3 is 12. Times 10 to the whatever, right? Notice here we've got 3 and 4, so 3 times 4. Notice here we've got 2 and 6, right? 2 times 6 is 12, right? And then here we're at 8, but that's 1.5 because 1.5 times 8 would be 12, right? So just, that's one way to do it. You could calculate the temperature along all of these points or something like that. But you can also do this if you wanted to show that it's isothermal. All right, I'm done talking, I think.